Hi, everyone, and welcome to this session on machine learning, reliability, and robustness. My name is Besmira Nushi, and I'm a researcher in Microsoft Research. Today in this session, we are going to discuss open challenges and ambitions and recent work on how to make machine learning more reliable. And today we will have three amazing speakers to help us frame this problem with their work and insights. The first one is going to be Tom Dietrich, who is a distinguished professor at Oregon State University, and he will talk about anomaly detection in machine learning. Next, Eja Kamar, a senior principal researcher in Microsoft Research, is going to talk about blind spot detection of AI in the real world. And then Suchi Saria, who is a professor at Johns Hopkins University, is going to share with us key insights about safely and reliably deploying machine learning in high-stake decision-making scenarios such as healthcare, but not only. So feel free to send your questions to our speakers as the presentations are running. They will try to answer your questions in the chat and maybe also elaborate on them afterwards in the panel Q&A.
It's great to have this opportunity to share with you some of my thoughts on the current status of anomaly detection in machine learning and computer vision. So anomaly detection is very important for trying to achieve robust artificial intelligence, and I wanted to review some of the use cases that arise. The first is open category detection. So imagine that we're training a self-driving car, and we've trained it in Europe, so it knows about deer and so on. But when we take it to Australia, what does it do the first time it encounters a kangaroo? That's an example of what's known as a novel category or an open category learning problem. And we can treat it as a kind of anomaly. The second is a novel subcategory. So we could imagine that we've trained a system that knows how to recognize dogs, but it actually only knows how to recognize beagles and golden retrievers. What happens the first time it sees a chihuahua? It might correctly get classified as a dog, but it should be much more cautious when it sees something that's very different from what it trained on. And another sub-area of research is known as out-of-distribution detection. And an example of this might be a medical X-ray analysis system that was trained on chest X-rays, but now at test time, someone feeds it instead of a front view of the chest X-ray, feeds it side views or back views, and it needs to detect that that's different and that it should not be trusted in those cases. So those are three examples where it's important for robust artificial intelligence. In addition, there are applications in data cleaning where we have a database of images, for example, but some of them were contaminated by noise of various kinds. Or maybe we're looking at cases such as fraud detection or cyber attack, where we also want to use anomaly detection. So there are many challenges in anomaly detection. First of all, there's little or no labeled data, and the anomalies themselves are typically quite rare, which is one of the reasons there's little or no labeled data. An additional issue is that the anomalies may not come from a well-defined probability distribution, especially in the adversarial case. So it doesn't make sense to approach them from a statistical standpoint. And the final issue, which comes up particularly in image type data, is what we call nuisance novelty. Not all anomalies are really relevant to the task or the use case. So if we're looking at internet traffic, for example, there might be lots of irrelevant novelty in the data that does not signal a cyber attack. Or in the image case, there might be changes in the background or the context that are not particularly important. So how do we avoid getting lots of false alarms in those cases? Well, for data that comes in well-defined features, there are three main technical approaches. The first, if we let capital D denote our training data, the first thing we can do is try to perform density estimation. That is, we learn a probability density, P sub D, that describes our data points. And then given a query point, XQ here, we calculate our estimated P of D and take its negative log, which is a measure of surprise from information theory. So if something has very low probability, then it will have a very large negative log probability. So one issue with this approach is that it is vulnerable to nuisance novelty because it tries to model all of the aspects of the data. And in high dimensions, it's really not statistically feasible to do that. A second approach is distance-based metrics. So if we can come up with a meaningful distance metric in our problem, then given a query, we can ask, well, how far is it from that query point to the nearest data point that we trained on? And this also is vulnerable to irrelevant or nuisance novelty because that influences the distance metric. One approach to trying to deal with the distance metric problem is projection methods. So imagine if we let capital pi sub k be a random projection, usually sparse projection into some lower dimensional space, we can apply our anomaly detection methods in those lower dimensional spaces and then aggregate them back to get an overall anomaly score. And this can go a long way toward dealing with the irrelevant features. And all of these methods can be, if we're training on contaminated training data, it helps to robustify them using things similar to the Huber loss, for those of you who are familiar with that. So my master's student, Andrew Emmett, has just completed a large comparison study where he used 19 existing UC Irvine data sets and compared 8 of the leading sort of feature-based anomaly detection algorithms, generating thousands of different benchmarks with systematic variation of various factors that we believe are important. But I just want to show here this plot, which is the mean effect of what's on the area under the ROC curve for making this decision anomalous versus nominal. And we see that the k-nearest neighbor algorithm, which is nothing fancy, actually gives the best performance. Now, the k-nearest neighbor method, it tends to be expensive to implement, but the isolation forest, iForest here, is almost as good, and it is much more efficient. And disappointingly, some of the most popular machine learning algorithms, like the one-class support vector machine, was the worst performer in this study. But I want to highlight that with the exception of one method, all of the other algorithms employ some form of a distance measure. And that's really the heart of the matter in trying to come up with good anomaly detection techniques. Now, the main challenge going forward is in the area of computer vision, speech recognition, other large complex signals, time series, things like this. And the challenge with these much higher dimensional spaces is that there are no easy distance metrics. Images, whether they, if you double the number of pixels in an image, you don't really change its essential content. So so there's a high degree. So that's one of the issues. The distance measured in the pixel space is not semantically useful. And it turns out that state-of-the-art methods really have troubles with images. For example, I'll talk about a method later that is trained on these images of faces of celebrities. And then when it's asked to make predictions on these numbers from Street View house numbers, it doesn't realize that they are not the faces of celebrities. So that shows just shockingly how badly anomaly detection methods can perform on image data. So I want to give a brief tour of 5 of the leading ideas. We have not solved the problem of anomaly detection in computer vision by any means, but here are 5 of the main ideas, and then I'll wrap up. So the first family of ideas are all based on just training a standard deep learning classifier. And so this is the typical organization of such a deep learning classifier, starting with the image over here and going through various layers, and eventually we end up with predicted probabilities, P of y given x. So y is the class label, and x was the input image. And the first thing we can do is use some measure of indecision. So if the classifier doesn't strongly recognize any of its known classes, then maybe that's a sign that the input is anomalous. And so we can use 1 minus the maximum probability that it predicted, or the negative of the entropy, which in the entropy will get large, or we get, actually, it shouldn't be the negative of the entropy, but the entropy as as an anomaly signal. Now, on theoretical grounds, this shouldn't really work, because a classifier that is trained just to predict P of y given x ideally would discard any information that was not relevant to making that discriminative decision. And but we see in practice this is a very surprisingly strong baseline method, which shows that our deep learning methods are not throwing away, finding only the critical information. The second approach is to focus on the so-called penultimate layer you can see here on the right, which is usually a much larger layer just before the classification. We can build probability models in that penultimate layer, and then we can score a new data point according to that probability model, and if it has very low probability, we could say it's an anomaly. A third approach, and one that's the most intriguing, I think might really lead us to a solution, are perturbation approaches. And these really came about from people studying adversarial attacks on systems, but these are not non-adversarial changes. But instead of computing an anomaly score for A of xq, the query, we're going to perturb xq by an amount delta q to try to reduce its anomaly score in some sense. We try to increase the score that it is assigned to one of the existing classes. And we find that if xq is near an existing class, the perturbation can substantially increase the predicted probability of that class, which is to say, reduce the indecision, the anomaly score. Whereas for anomaly points, these perturbations have much less effect. And so this is currently probably the leading strategy. Another family of methods are based on what are called autoencoders. These are deep neural networks that take an input x, map it into some restricted reduced space z, the latent space, and then map it back to the input space with a function g, the so-called generator, and then compare x tilde there on the right to the x value that we started with. And the difference between those is known as the reconstruction error. And also there are groups that try to fit a probability model in this z space and then use a latent probability model. While this is very elegant and works well in small spaces, just using principal component analysis as a technique, in deep networks, it hasn't produced very good performance. Another strategy that's somewhat related is so-called normalizing flow models. So there are techniques for deep density estimation, and these are based on learning invertible functions, f sub phi of x. And there are some very general nonlinear neural network style functions that can be developed, and you can convert a density over this mapped space, f of x, back into a density over p of x by using a normalization using the Jacobian, which is easy for us to compute with our deep neural network techniques. And then we can compute an anomaly score again as the surprise. But this is an example of a method that fails miserably on the celebrities. So down here we see these are the training data, and on the horizontal axis here is the log probability. So larger values are to the right. And so you can see that it's actually assigning higher probabilities to the street view house numbers than it is to the celebrities' faces, which is totally the wrong thing. That the red points should be to the left of the blue, not to the right. And this was quite a shocking discovery that was uncovered just last year. So there are another family of methods that try to learn distance functions. So we take two data points, xi and xj, and map them using this function e, the encoder, into this latent space. And then if xi and xj belong to the same class, we try to move their z points close together. Whereas if xi and xj belong to different classes, we try to push their z points apart, at least by some minimum amount. And then the hope is that we can use a nearest neighbor classifier in that space, and we can also use that distance to find anomalies. Unfortunately, we find that anomalies tend to be mapped very close to the normal points that the network has been trained on. So again, this doesn't work as well as we would hope. And the last idea, and maybe the weirdest, is the following. We define a set of auxiliary tasks. And these are typically things like rotating an image by 45 degrees or 90 degrees or 180 degrees, and flipping it and stretching it and things like this. And when we train a network that given the image to which a transformation has been applied, the network simultaneously tries to predict what class label the image should have and also which transformation was applied to it. So for example, the digit 3, we might rotate by 45-degree angle, we will get that kind of transformation. And we would like the network to then output that a high probability for that particular transformation, as well as predicting that it belongs to the class 3. So then given a test query, we can apply these different transformations. And if the transformation subnetwork, this part here, if it is correctly predicting those, and we know what the right answer is because we applied the transformations, then we're willing to trust that its classifications are also trustworthy. But if it can't predict the transformations, then we'll declare it to be an anomaly. And the intuition for what's going on here is that in order to understand that this 3 has been rotated, you really have to know what a 3 looks like in its normal orientation. And so it seems to force the classifier to pay attention to what's important in the image. And this also helps remove some of the nuisance novelty. So in conclusion, anomaly detection is very important, critical for building robust AI systems. And also it can support practical applications such as fraud detection. But it's also very difficult. Fundamentally, virtually all the methods rely on some notion of a distance. But this is very challenging for images because we need some notion of semantic distance, and our deep neural networks don't directly give us that. I guess reasons for hope are that research in this area is advancing very rapidly, but with relatively little theoretical understanding. So I'm hoping that in the near future, we'll understand much better why these methods are succeeding or failing, and we will really be able to address this question of anomaly detection for robust AI. Thank you very much.
My name is Ajay Kumar. I'm a senior principal researcher at Microsoft Research AI. Today, I will talk about the challenges that arise from having AI systems functioning in the open world. I will also discuss directions towards improving the reliability and robustness of our systems, guided by the work we are doing in the company towards developing responsible AI. I don't need to tell this audience about the advances in the field of AI. We see machines reaching human-level parity or even exceeding it for tasks like speech recognition, object recognition, when these systems are evaluated on static benchmark test sets. We are also seeing these systems mastering games like Go and Pac-Man. As AI systems are being used in domains that matter for our society, like helping with legal decision-making, medical decision-making, or having self-driving cars on the roads, we acknowledge that the behaviors of these systems, in particular how they fail, have consequences for our society. Recognizing the impact of AI systems for our society, in 2016, Microsoft released its Principles for Responsible AI. These principles talk about having fair systems that are reliable and safe, that respect people's privacy while being inclusive, accountable, and transparent. However, stating these principles is the easy part. Ensuring that company practices agree with these principles has been the challenge that I've been working on with many of my colleagues at Microsoft Research. We organize our work in this space around a company-wide initiative called Ether. These are the initiatives we have for developing responsible AI. My efforts in this space has mainly focused on reliability and safety, understanding the limitations of AI systems, and thinking about scalable approaches for addressing them. I'll start my talk today by discussing 3 main insights I gained from being involved in this company-wide initiative. Then I will briefly present 3 research projects that are guided by these insights, and I hope you will see the connections. The first insight I would like to share is that making progress in responsible AI stems from understanding the different limitations AI systems have, the way they fail, but not only in the lab conditions, but also when they are deployed in the open world. The way AI systems are evaluated through aggregate performance metrics today on static test sets hide the complexity of the real world. In the real world, we see that training data and models are almost always incomplete and lead to failures. We also need to worry about adversarial attacks and the errors that come from the humans that these systems are interacting with. Understanding the different ways AI systems fail is important as we think of different ways to make AI systems more reliable and robust. The second insight is that there is no silver bullet solution to address the different kind of limitations we see in the AI systems today. However, we see a variety of emerging techniques that can be used together in coordination towards this goal. Most work in the AI community focuses on algorithmic advances to improve model reliability and robustness, and I'm confident other speakers in this session are going to be sharing work from this space. The point I would like to make, though, is that it is important to acknowledge that AI systems do not exist and function in the world alone. They exist in a larger ecosystem in which they are developed, deployed, and function in. We know that AI systems are developed by people, they learn from data provided by people, and they also work with people in the real world. Therefore, opportunities to overcome the limitations of AI systems should also take into consideration how to empower the people involved in the development and deployment of AI systems. Finally, the third insight I would like to share is that we need to align our efforts in the responsible AI space with the way these systems are developed in practice. To understand the challenges that ML practitioners face in this space, last year we did a large-scale survey with more than 500 machine learning engineers at Microsoft, and the findings were very interesting. The survey revealed that the practitioners lack sufficient tools, in particular for testing, debugging, and evaluating AI systems. We see that concerns around reliable AI are not only about model development. Attention should be paid through the life cycle of an AI system, from design to development to deployment, and continuous monitoring and improvement of these systems. So today, after sharing these insights, I will briefly talk about 3 research projects that are guided by these insights and observations. The first project will be on explorations of AI limitations, explorations of how these systems fail, and what are the reasons behind it. Then I will talk about how we are turning our learnings into tools for developers to use for error analysis. And finally, I will talk about reliability considerations on backward compatibility when models get updated during AI lifecycle. Let's start with blind spots of AI systems. When we look closely into the performance of AI systems, we see that in many systems, failures are not random, but they are in fact concentrated around some input spaces. A great demonstration of this comes from the gender shade study performed by Joe Bolomoni and Timnit Gebru on evaluating the performance of common gender prediction models across the groups of gender and skin color. They show that large performance discrepancies of these models can exist when they are evaluated across these different groups. The question is, why we are seeing such disproportional error rates, why we are seeing so much high error rate for women with darker skin color compared to lighter skinned men. In our work on blind spots, we explored the role of data incompleteness in understanding disproportional error rates in AI systems. So let's get to the fundamental assumption of supervised learning. The fundamental assumption of supervised learning is that our training data is a complete representation of the real-world concept we are trying to learn. This assumption breaks down when we have blind spots in data. So in this hypothetical example, let's say we are developing a classifier of cats and dogs, and in the world there are many different kinds of cats and dogs a machine learning classifier needs to learn about. Let's imagine that the training data lacks sufficient representation of small dogs, but it has sufficient representation from small cats. What the model ends up learning is associated every small animal with being a cat. We call these types of errors unknown unknowns, and the spaces with high concentration of unknown unknowns as blind spots of AI systems. In our AAAI paper, we present a human-in-the-loop technique for searching for unknown unknowns in unlabeled benchmark data. The proposed technique involves two steps. The first step is called descriptive space partitioning, and the second step is a multi-arm bandit-based approach for guiding the search. In our paper, we show that this technique can create an interpretable representation of blind spot spaces and can find unknown unknowns more efficiently than simple heuristics. And you can find the details of both experimental results and the techniques in our AAAI paper. Next, I want to talk about how we are turning these insights from this AAAI paper into an easy-to-use tool for ML practitioners. Discovering the blind spots of AI models is the first step towards improving these models. We really need to know where these models are failing to be able to fix them. In fact, after performance disparities in face recognition models was discovered by researchers, the relevant teams at Microsoft took the necessary steps to increase their data diversity for this application, and the resulting models had close to equal performance across gender and skin color groups on benchmark datasets. As our survey of ML practitioners have shown, the challenge here is empowering the developers with the right tools so that they can discover these blind spots efficiently as a part of their daily routine of the way they evaluate AI systems in practice. The current practice of evaluating AI models focus on aggregate metrics, for example, aggregate accuracy or aggregate AUC, which hide the structure behind how failures happen in these models. In this example, the aggregate evaluation may tell us that the model is 73% accurate, but we don't really know where these errors are concentrated. Are they random, or are they part of a subspace of the test data? And most importantly, what is the most effective action to improve model performance to get this accuracy to a higher point? These aggregate metrics hide all of this information. What we try to do in the Pandora project is using interpretability techniques to discover how the model performance varies across the different subspaces of data. The goal is developing these techniques into a tool set that help engineers accelerate the development iterations by identifying errors faster, more rigorously, and systematically. The workflow of our tool set is pretty simple. It starts with a benchmark dataset. If the data already has human interpretable attributes in them that can correlate with the errors, that is great. Otherwise, we recommend a feature augmentation step to enrich the dataset with such attributes. We run the ML model we want to evaluate on the benchmark dataset and collect error labels indicating which instances the ML model is correct and which instances the ML model is making mistakes on. Then we use interpretable machine learning techniques to automatically learn patterns that can best separate the errors from the successes. The tool provides views at different levels to help developers explore what the error spaces are and develop hypotheses and then come up with actions to improve these models. Let me demonstrate how the tool works for error analysis of the gender shades dataset, where the dataset is augmented with high-level human interpretable features. Although detecting gender from face images might not be a great idea after all, we'll look into these models for the sake of understanding the different types of errors that can creep into the model because the training data is not representative enough. Okay, here we see a view from our tool. On the left side, we see different features that are going to be used for exploring the errors. And here you see ground truth features like gender and skin tone, and also automatically inferred features about the facial hair, hair length, accessories, age, and so forth. And we generate these predicted features from Azure Cognitive Services. On the right-hand side, we see a decision tree that was trained to predict system failures based on such features. Basically, what the tree is doing is it is trying to separate success cases from failure cases. The nodes of each node, the color of each node, represents the error for that particular node, and we can follow the critical error path by following the darker shades of red to see how the error rate in this model is increasing when we get into different subspaces. So the overall error rate of the model on this data set is around 5%. But it becomes higher and higher if you are a woman. Now we have the error rate of 11.48%. And if you have no makeup on, now the error rate becomes 23%. And if you have short hair, and if you are not smiling. In fact, the error here increases from 5% to 35%, and it is revealing these hidden conditions of failure that the low-level aggregate analysis would not be able to discover. Of course, not all important features that relate to errors are not part of this data set, so it is very important to empower the developer to be interactive with the tool to develop hypotheses. So for each node of the tree, we enable seeing the failure and success instances side by side, so that developers can engage in an interactive way with analyzing errors, developing hypotheses, and thinking of ways for improvement. Finally, on the last project, I want to discuss that model performance is a consideration through the life cycle of an AI system, and we need to pay attention to the backward compatibility of AI systems during updates to ensure such reliability. Reiterating what I said earlier, in real-world systems, AI models do not function in isolation. They are part of a larger ecosystem where they work with other ML components or traditional software components, interact with other systems or with people. This integrative nature brings up additional considerations for the reliability of AI systems, as AI models and other components take dependencies, people build expectations and trust on the AI systems as they are working together. This issue of how these dependencies, trust, and expectations are affected, the issue is all of these dependencies, trust, and expectations are affected when a model gets updated. ML practitioners update models to improve model performance. For example, ML practitioners may increase the dataset size or add more features, or may decide to change the architecture in the hope of achieving higher accuracy from these models. However, increased aggregate performance does not mean that the new model is backwards compatible with the old model that was functioning in the world already. So what I mean by the backwards compatibility is that the updated model can make new types of errors that the old model was not making, breaking backward compatibility, thus breaking trust and dependencies. These sort of compatibility issues introduce risks of reliability. Why? First, when we are introducing new, previously unseen errors, this can break the error handling we have deployed or developed in our systems. Imagine models later in the pipeline are trained to actually handle the errors of the earlier components. When earlier models get updated and now they are making new types of errors, the error handling of the later models become invalid, and now errors can propagate through the integrative pipeline and result into errors. Second, incompatible updates might create maintenance issues, especially when components take dependencies on each other. For example, imagine the later components were trained to optimize the accuracy, knowing about the errors of the earlier models. Now, the earlier models get updated, we need to update the whole pipeline, which may become infeasible. And finally, when we are putting models into the pipeline without backward compatibility, this may actually require doing all the testing, reliability tests all over again, which increases the workload we have for testing. Backward compatibility issues also arise in human-AI collaboration as well. When AI systems work with people, users develop models of trust. Issues with backward compatibility can break user trust. As an example, this particular article discusses how users of Tesla cars develop mental models about when to trust these self-driving car functionalities, and when model updates happen in a non-backward compatible way, this can break user trust and create usability issues. The main message from this discussion is that improving accuracy is not the only metric one should care about when we are updating our AI models in systems. Here we propose looking at compatibility scores as well in order to understand whether the new version of the model has introduced new errors. This definition is saying that the updated model is fully compatible with the older model if all the instances that the old model was getting right, the new model is getting right as well. However, one can ask, isn't backward compatibility something that comes naturally in machine learning, especially if the update is simple, like just adding more training data into our systems? In fact, we see that compatibility is not built in. Here we experimented with 3 different data sets in the domain of high-stake decision making, respectively recidivism, credit risk, mortality at hospitals, and so forth. The update here is as simple as just increasing the size of the training set, and we see that model performance improves with an update as expected. That is what we expect. But there are even cases when compatibility can be as low as 40%. What 40% compatibility means is that the model is now making a mistake on 60% of the instances it was before getting right, creating a big issue on expectations and trust when these systems are updated in the real world. Now that we have quantified compatibility for model updates, we can incorporate that metric into our model training as a regularization factor to penalize incompatible updates and actually get more compatible updates as a result of model training. In this new formulated loss, lambda controls a trade-off between model compatibility and final model accuracy. By varying the lambda value from low to high, we can create different classifiers that vary in the performance versus compatibility spectrum. Here, the y-axis denotes the performance of the updated model, and the x-axis denotes the compatibility score, and the dashed line represents the performance of the original classifier. When we set lambda to a very low value, now we are not putting a lot of emphasis on compatibility, so we are getting a high performance model that has a low compatibility score. If we set lambda to a high value, then we get to the point on the bottom right corner where it has a high compatibility, almost a perfect compatibility, but we are not really getting the accuracy gains we would expect to get from a model update. But when we use intermediate values for lambda, we get these curves for different regularization losses we have tried in this project. By increasing the weight of the lambda, we can increase the compatibility and see the effect we have on the final accuracy of the classifier. This indicates that there exists a trade-off between compatibility and model performance of the update, but also we can see a flat region, especially if you look at the blue curve, where we can gain a lot of compatibility benefits without sacrificing any accuracy in the updated model. So we are actually getting compatibility back for free when we introduce this regularization factor into our updates. This gives developers a tool they can use to minimize the number of new errors while maintaining performance. To conclude, we have to acknowledge our responsibility in developing AI systems, since the way these systems function in the world have real consequences for our society. Understanding the limitations of existing techniques, processes, is an important step in finding ways towards more reliable, robust, and safe AI systems. While it's important to invest in algorithmic advances in this space, we need to consider the larger ecosystem that are involved in training, developing, and maintaining these systems, and also invest in tools, design practices, design guidelines, frameworks for empowering both AI developers and users of AI systems. Thank you for listening, and I'm looking forward to the panel discussion.
Hello, everyone. I am very stoked to be here, and I'm going to talk today about implementing safe and reliable ML, and especially new developments in this research area in the last few years. As machine learning is making its headway into more and more fields where especially fields like healthcare and education, where there are massive consequences into life decisions, very crucial life decisions are being made using software. It's very important for us to make sure that the software we're implementing works correctly, works the way we expect it to behave. It's not biased in any way. And so this notion of thinking about how we get there is crucial. And so as examples, here I'm showing you a study that was done out of Mount Sinai where they showed X-ray images of a chest scan, where you're using the X-ray image to automatically identify patients who have pneumonia or don't have pneumonia. And turns out you could actually develop a really nice algorithm that could identify these patients with the pneumonia diagnosis very accurately. But the challenge is, the way they developed it, it was very easy to obtain an algorithm that was very sensitive to a specific hospital. So it worked really well in 1 and 2, but didn't work so well in a third hospital. And when you looked into why, turns out it's because it was learning strange things about the scanner that was used within a particular hospital that didn't generalize as you move from one hospital to another. Another example is predictive policing in LA, where the police department there was using machine learning algorithms to identify what are neighborhoods where they could monitor more intensively. And if they could predict which neighborhoods are likely to have crime on a particular day, they could start, preparing the workforce to go there. But the challenge was that as they did this, they were introducing feedback loops in their data, where the more they monitored, the more, more of the workforce they sent to specific neighborhoods, the more data they got. The more the ML algorithm learned that those are the areas with more crime. And so there was this unfortunate reinforcing loop. Third, very simple example, like a very common example in machine learning, where, on the left and right, these are two images of a panda, which to most humans look exactly the same. But oddly enough, a little bit of noise, which is what you see the image in the center, if you add that little bit of noise to the panda image, you produce the image to the, as the output, which again, like I said, humans can't tell the difference, but for machines, they would behave very differently. So the image on the left, it thinks, this image is definitely a panda, and on the right, it thinks this image is a gibbon very confidently, which is very odd and would be very confusing to a human expert user who'd be using, say, machine learning to start making decisions. So I gave you like a collection of decisions, like here's a last example. There are many more. Here's an example where, this is in a hospital setting. We're using data to be able to identify and predict adverse events like sepsis. But turns out over time, as practice patterns for doctors, how they prescribe certain labs and procedures change, these model behaviors don't generalize, or models can model performance can deteriorate and perform poorly if, for example, they're very used to relying on a particular lab test being there, and over time practice patterns change and those lab tests are not there. And so how do you think about, building machine learning systems or that are actually robust to these kinds of changes? In the very worst case, we want to know when these kinds of issues are happening, so that if it does occur, it isn't sort of leading to incorrect judgments or incorrect predictions or incorrect decision support, causing, obviously in healthcare, this could do something as bad as actually, like, unfortunately harming patients. So this introduces the first most important concept, which I think in machine learning, a lot of excitement has been around model development, model training. You take a data set and you develop and deploy a model against that data set. But what we've missed, which is very common in other areas of engineering, like civil engineering, nuclear engineering, these engineering fields where safety being safety, these are disciplines where safety is crucial, and you're designing systems in these disciplines. There's a whole understanding of how do you design for reliability. And so the equivalent concept here is, let's think about what is ML reliability. So in the ML sense, it's, how do we build ML components such that first, we understand how should they behave. Second, then they're behaving the way we expect it to behave. And we understand when is it likely to misbehave, when is it robust, when is it not robust, when is it behaving in biased ways. And because machine learning software or AI software depends a lot on data points that are inputs that we have no control over, the unpredictable or stochastic nature of those inputs make this notion of studying ML reliability quite hard. Different from sort of deterministic software, you can exactly dictate how the software should perform in particular settings. And ML reliability right now is getting confused by this notion of the kinds of bias that emerge out of poor system design. So fairness and ethics. So we still have to think hard about, when we're going in and designing a system, thinking about, is the system that we're designing fair and ethical? We need to understand, to be able to answer whether a system is fair and ethical, what does it mean to be fair? How do we, are there any harmful, unintended consequences from us designing in a particular way that makes it unfair? And reliability goes one step beyond that, which is once we've designed a system that we think, we want the system to behave in a particular way, we need to be able to guarantee that it behaves that way in the, when it's being applied in an everyday setting. And this is like other system requirements like privacy, security, and other system failures we are used to thinking about. So in thinking through reliability, and again, borrowing from other fields where, of reliability engineering and other aspects of engineering, there are three key areas. First is failure prevention. So how do you ensure, build your systems in order to be more failure-proofed, which means you're learning from data and you're designing systems to avoid, you're upfront identifying high-risk failure points and you're designing them to be robust to those failure points. The second aspect of this is test time monitoring, which is, as you've deployed them in real time, you're able to monitor and identify when failures might exist in real time and be able to do correction. And then the third is maintenance, which is how do you actually maintain these systems over time? Now, these are three areas that I think actually in the field of machine learning, last few years, there's whole new threads of research starting to emerge. But overall, we don't approach machine learning research this way and machine learning deployment and applications this way. But I think in each of these areas, there's numerous possibilities for actually developing new algorithms that can allow us to make these systems more robust. So let's now imagine we have this framework. I want to talk a little bit about one of these areas, like failure prevention. And in particular, what are some ideas we're thinking about in failure prevention? So can we develop learning methods that proactively learn to avoid failures? So one big misunderstanding, and this is especially true outside the field of machine learning, when there are practitioners employing machine learning, like for example in healthcare, there's this discourse that AI and ML are inherently biased. AI and ML are not inherently biased. These are just what algorithms do is they take data as inputs and they produce certain outputs. Nothing about this particular process or construction is biased. It's the way we design it that can yield biased algorithms. So for example, if people naively take some data, don't check for how good the data is, don't check for how biased these data are, and they don't do any kind of correction, then you're going to get into producing algorithms that are biased. So you can actually train algorithms to anticipate and avoid particular types of failure. And there are several threads of research here. So for example, there's these types of biases, like the panda problem I mentioned is this notion of, those are called algorithmic blind spots, specific types of noise where the algorithm misbehaves. And there are whole learning algorithms or paradigms that allow you to train and develop models that are robust to that kind of failure. So adversarial robustness is that what's called. Similarly, shift-stable models that are more immune to failures. So another type of failure, like the predictive policing example, the practice patterns changing in hospitals, those are examples of data set shift and failures due to data set shift. So there are shifts in the underlying population or feature sets or the practice patterns. And as a result, when these shifts occur, naively trained algorithms are not immune to them. They start, model performance deteriorates. But you can train these notions of shift-stable models that are more immune to these kinds of failures. And I point to a tutorial below that sort of overviews kind of overall these three categories and examples of types of algorithms people have been pursuing in each of these areas. I've also listed, if you're curious, some example papers if you want to learn more about how people are using notions of causality and notions of like techniques, algorithmic techniques for being able to prevent failures in learning these kinds of stable models. Finally, sometimes algorithms are biased because of poor study design or human error. So for instance, if we're not careful in designing the right kinds of algorithms, the resulting, product is going to be biased. So here's a recent paper that showed that, Optum, which is a healthcare company that was using algorithms for the last 10 years, they've been using these algorithms to determine in the, among the sickest patients or like the high risk, high cost patients, which patients should get extra assistance in order to prevent them from having complications that end up leading them to the hospital. And turns out the algorithms they were using, the way they developed it, was racially biased. So it was much more likely to prescribe care to white patients than Black patients. And part of it had to do with something, if they had realized, was easily correctable. It's just that at the time of development, they didn't realize that the objective function they were using for training was emphasizing identifying high-cost users instead of the sickest patients. Another example of human error is, a very well-cited example where face recognition algorithms that people are developing on data sets that have a lot more white faces than Black faces or more men than women. In this example, they showed, lighter males and lighter females had much more coverage than darker males, darker females, especially darker females. And as a result, the performance of the algorithm was very varied, and it it performed much more poorly in recognizing Black female faces. And so this obviously, again, at the time as they'd realized it, could be corrected for. But so some of it is by enriching your data set, some of it is by better study design, like in the Optum example, and then a lot of it in more subtle cases like practice pattern changes, like not all of it, but you can anticipate, you can design more clever algorithms that are more stable to those kinds of changes. This is a growing field with many new techniques emerging. And I think it's crucial as you're employing these kinds of methods in your own setting to think about the degree to which the software you're deploying is robust to the different kinds of failures that can occur in practice. And then finally, a third thing, and this is especially important for people when they're first moving from research into translation, which is, developing an algorithm for a new use case where you can take your data, you scrub your data, you clean your data, and you're training a first cut of an algorithm and producing a first, what I call the AUC, the performance characteristic like an AUC, sensitivity, specificity, first time. And you can do a couple of tweaks and get to a pretty happy place where your overall metric like an AUC looks really nice. But to get from there to an actual usable system where you have real users, like, so I'll give you an example in our setting, we're building and deploying algorithms that are being used by clinicians, like doctors and nurses, in assisting with decisions around complications that providers often miss, doctors and nurses often miss. And so what we found is, you can take a data set of patients and show pretty high quality performance. But then when you start deploying it in the practical setting, you start realizing that what it takes to get pretty good AUC to actually case level accuracy and case level actionability is actually a whole lot harder. I would say, from my standpoint now, when I think of going and attacking a new use case area, I think of it as maybe if I have all of my algorithmic tools available to me, let's say I take 1 month to develop that initial result that looks pretty good, going from there to something that actually is good enough on a daily basis that doctors and nurses would trust it is more like maybe a year and a half worth of effort after that. So huge amount of effort in going from, and this is sort of a misconception where if you've never actually translated these algorithms, something that's often missed, but it's super crucial, again, when we think of areas where like healthcare, education, social justice, where there's real consequences to not being right. And if your users are expert users who are really busy, they're going to, probably not trust it and not adopt it if they don't feel the quality in their daily experience is very good. So again, in this aspect of validation, I think there's enormous research opportunity because, we spent as in a field a whole lot of time thinking about new algorithmic training methods. We spent not as much time thinking about how do we, improve model validation? How do we improve monitoring at test time? And so here there are some lots of super interesting new research coming out. A couple of papers I note at the bottom where there are ways in which obviously one way to think about it is as you deploy the system, have a team of humans review every so often a case that comes out, maybe so that you can identify if they see anything, maybe 1 in 5 cases are reviewed. This is obviously very expensive and very cumbersome, but critical. And so then algorithmically, maybe the way to make this whole process smarter is if you could identify cases where you're more likely to be wrong or the system is more likely to be wrong or system is more likely to produce untrustworthy results. Now you can go and only review those. So that's sort of this notion of what I call test time auditing or real-time auditing of outputs and individual predictions, and a second algorithm can run and monitor to see if it can be trusted or not, and you can audit to see if it's correct using a human in the loop. And there's beautiful work going on in the field where people are, trying to develop ways to make the audit simpler and easier by identifying what would be the reason, by building interpretability and transparency into the system. Finally, I think it's so important we bring discipline into how we validate. I think we should really be treating algorithms like prescription drugs, where we conduct forward-looking trials. One of the challenges here is that algorithms, unlike drugs, aren't frozen. They evolve over time. So we really need much more sophisticated frameworks to be able to monitor for how good this algorithm is, how is it performing over time, as the world around it evolves, as practice patterns evolve, as the data evolves, as the population underneath that's being monitored evolves, and for us to be able to identify in smart ways when the system performance may be deteriorating so that we can actually do something to fix it. With that, I'll end. Here are some example papers if you're curious to read some more from our lab. And with that, thank you.
Okay, here we are back again. Thanks everyone for the great talks. I thought they were very much aligned and they were all bringing different perspectives of how we should be seeing reliability and robustness. So why don't we start by warming up with the definition of robustness? I know it came up yesterday in the security and machine learning session. And there was sort of agreement in the panel that we are having a hard time to define robustness. I don't know what your thoughts are, and maybe if you have on top of your mind aspects of robustness that maybe we are not paying enough attention and that you want to bring up so that we have them more in our radar. Let's start from maybe Tom.
I guess I would start by talking about the distinction that I think Suchi raised between anticipating problems and making sure the system is invariant to them versus doing the runtime monitoring. Or maybe it also came up in HA's talk. You know, the anomaly detection stuff that I was talking about is really for runtime monitoring, and so it doesn't make the machine learning system any more robust than it was. It only, I mean, it tries to close the barn door after the horses have escaped, in some sense, right? Mm-hmm. And detect that there's a problem at runtime. So I would define robustness as the former, that we identify some collection of threats or challenges or problems, and we make our system invariant to those so that it won't be affected by them. I think a sort of deep intellectual question is, sometimes it seems that by making the system robust to certain problems, we, as a side effect, gain robustness to other things that we didn't anticipate. Whereas other times, when we make the system robust, we actually induce brittleness in some other direction. And this is a big mystery right now. So there was a talk at ICML that showed that one way to try to make a machine learning system more robust to these adversarial examples like the panda is to force the system to be invariant in some sort of a epsilon ball around each data point. So if the data point were perturbed, then it would still give the same answer. But what this tends to do is make the system very confident of its classifications in that ball, and then as soon as you step outside the ball, it's still confident, but now it's no longer robust. So you get sort of a bad combination. So there was some work. This is Matthias Hein and his students on trying to get the confidence to drop as you get close to the edge of the ball, so that it doesn't it's not overconfident outside the ball.
Mm-hmm. So this brings up the continuous testing and monitoring, and Deja was actually talking about this in her talk, and even it came up in the chat in the questions about how this is an iterative process, and maybe there is no silver bullet, but we need to think about different tooling.
Yeah. There's definitely a difference between robustness of machine learning models versus robustness of the system we are developing. I think the robustness of a machine learning classifier is a very technical definition where you talk about how your training set generalizes to unseen test instances and what that really means. However, when we actually get into real-world deployment, then we are not only thinking about one decision boundary and the robustness around that decision boundary, we are actually thinking about the whole AI development lifecycle and the data and the people that are involved in that process, and the many ways that people have to be supporting that process with the outlier detection methods that Tom was talking about, or the careful thinking that Suchi was talking about in her talk about like what it really means for things to be biased or unrobust. In the real-world implementation, robustness actually is a very human-centered concept, because there are many things that machine learning models can be robust to, but the things we really care about are the human expectations. What are the expectations of the users that are using these systems? And what do they expect as reliable? Because as humans, we get fooled too. If you change all the pixels on an image, for example, from like a gibbon to a panda, the human will not get that image right as well. So there is definitely an expectation question in our definition of robustness. And what are the cases that we expect our systems to work reliably? And what are the kind of shifts that we might be able to tolerate because we know that these are just reasonable errors that all organisms are going to be making?
And there is this other aspect that Suchi was mentioning towards the end of the talk about how certain changes in the environment or the way how people are using our systems may introduce these shifts that are not really initiated by the data that we have collected beforehand, but from the interaction itself. And it seems like this type of shift is more subtle. Perhaps it doesn't even happen in one single day. It may take some time until we see it. Based on your experience, Suchi, like when you deploy these systems in the real world, what do you think we have in hand now and what we should do next to do this monitoring?
Yeah, so I want to start with the first question you asked and kind of building on what Tom and Aja said. I think part of what we lack as when we're thinking about end-to-end systems and deploying end-to-end AI systems, which is really sort of at the goal at the end of the day, right? We're building algorithms in order to be effective in influencing the real world and succeeding and solving life problems better, faster, more effectively. I feel like thus far, our research parlance has been all around understanding performance on a data set, which is where we've come up with a lot of the terminology. And as soon as you move from one research data set to the real world, like Aja said, you have to think about end-to-end systems. And I think we lack the framework for even thinking through what are the components here, where, what are the things that matter? What should we be measuring? How should we be measuring what we look for to test whether something is good or not good? And I'm using the word good and not good because good and not good is sort of a qualitative term we know how to think about. I feel like robustness is a very statistical concept, historically has been narrowly applied in a very particular way. And we need both qualitative and quantitative understanding of good in our scenario, right? And so when we look at other fields, like other safety critical fields, like nuclear engineering, civil engineering, where if you screw up and you build things incorrectly, it costs lives. People have whole disciplines around it. So that they think about this concept of reliability. And what does it mean for a system to be reliable? And what are the phases or processes people put in place in order to make things reliable? And they talk about sort of these three pieces. One is failure prevention, the ability to be able to build learning algorithms that prevent failure, which speaks to our desire to construct these robust learning algorithms. Second is the ability to monitor over time. And then third is to adapt over time. And all of the above are absolutely critical. And I think right now we sort of still are very much like limited to this one data set. And if you look at the field as a whole of like failure prevention, reliability as a whole and reliability monitoring as a whole, then we start to think beyond just the learning piece and thinking about ongoing monitoring, auditing, and the kinds of ideas. And for each phase, there may be totally different metrics. So for example, when we're trying to build an algorithm to be robust for a particular domain, we want to anticipate what are all the failure points and to build a learning algorithm that prevents those failure points. But the reality is the world is continuously shifting. And if the world is continuously shifting, we want to be able to build monitoring tools that allow us to identify on the fly when things are going wrong. So now to just answer to your very specific second question, I think the tools are very domain dependent. There are sort of broad tools, like you could put a way by which you measure AUC on a continuous basis or predictive performance on a continuous basis. You could measure stats about your data on a continuous basis. But then there's sort of domain-specific measures, which I think are, at the end of the day, the most important, because those are motivated by where getting things wrong is actually very costly and problematic. Does that resonate? I also have to. I'm going to be just for a minute. I have to escape, but I'll be back. I'm here.
I would like to add one thing to what Suchi said about being, evaluating ourselves on static data sets, because this is what we report in our papers. This is what is celebrated in the press when we, get a benchmarking success. However, that creates a lot of expectations from the practitioners of AI who are actually looking into the academic world and asking the question of what are the big trends, what are the big innovations that are happening right now so that I should get them into my system immediately to get that competitive advantage. And they are setting expectations based on numbers that are computed on that static single data sets, and where everything looks great, where papers do not really discuss what happens when there are distribution shifts or the training data set do not exactly match the real world use case that practitioner have in mind. So us not answering the questions when we are reporting our successes on robustness, reliability, actually sets strong expectations for the practitioners of machine learning and can increase the gap between what academics talk about and what really happens in practice.
Yeah, I just to echo some of these points in terms of what should we be monitoring after deployment. I think that's also a very tricky question because we've seen that after we've deployed some systems, the whole technical community, there were unexpected feedback loops set up. For instance, in recommender systems, which were formulated as making a one-shot recommendation, but were deployed in a loop. And so it didn't occur to us to measure the dynamics of that loop over time. And I really loved HA's decision tree showing where mistakes are being made, and that's an example of something we should always be monitoring to see if we're expecting to see certain mistakes in certain areas. And if those are, if we're seeing mistakes in new places, our overall error rate might be fine, and our area under the ROC curve or whatever might be fine, but the distribution of our mistakes might be shifting. So these are tricky things. I don't know how to hand the ball to Suchi, but one of the things I think is really beautiful in the work that she mentioned on this causal transportability is really methodologically asking the developers and the subject matter experts at the time we're designing the system, what do you think are the ways that the world is likely to change? And let's try to elicit those early on. So maybe you can talk a bit more about that, Suchi.
Sure, Tom. Yeah, thanks for bringing up that work. So I think overall, thus far in learning algorithms, the way we've thought of, like generally the way machine learning as a field has approached it is we take a data set and we have some error metric in mind. And with that error metric in mind, we fit in a learning algorithm to optimize it. But this is kind of shifting the way we think about learning to say, in addition to optimizing for performance on this fixed data set, we also want to think about what is the system actually trying to do, in which world is it looking to operate. And in that world where it's looking to operate, can you think about what are some properties or invariances it should have? Like it should behave, it should be okay if certain types of, so I'll give you an example in the context of medicine. Let's say I'm developing a way to identify a disease like sepsis or pneumonia. I want my algorithm or the system to be good at diagnosing this, even if there's some change in the way providers order certain types of labs or order certain types of medications or order certain types of, and why is this important? Because, people change all the time, behaviors change. And if some change happens that my algorithm is susceptible to that I wasn't anticipating, then suddenly my diagnostic performance deteriorates without me realizing, and that could really cost lives. So if we know upfront, there are all sorts of like changes in behavior, changes in ordering patterns, changes in subpopulations that we know it should be a robust invariant to. You can build that in as properties around, invariances you hold to C and develop learning algorithms that are then invariant to it. Now, if you extend this idea all the way to, to think through what are all the causally, when you think of like invariance, you can start thinking of like what is just causally true. Like, like when you get a bacterial strain that leads to bacterial flu. You can't get a bacterial flu without a bacterial strain. There are just some truths in the world. And if you work through all the truths in the world and enforce those truths in the world, what turns out is you just get more robust learning algorithms and learned outputs. And so the whole idea behind transportability is this notion of identifying what are truths in the world that you know to be true and you would expect to be true and you would expect to be invariant to. Those are often causal facts in nature. And so if you can enlist with domain experts those causal facts and build algorithms that enforce them, you'll, as a result, end up getting something that is more robust. So that's sort of the concept. And turns out you can actually prove a lot of things about this. You can show bounds in terms of, not they're sort of, these algorithms are stable, they behave well, they perform well in terms of when you shift and change the data set around.
So there is a question, Suchi, about like how do we discover together these truths about the world? because it feels like we have a separation now in the way like where machine learning is created and built and deployed and who is using it. So if you give me a data set on medical data and I am the one who has to discover these truths, I will miserably fail at it because I don't know about this truth. How do we work together with professionals and so that we can encode these things back and forth?
So I think most real world systems, when you when we develop learning algorithms in the research community initially, we used to think of this as, look, here's my data set. It performs really well. That's exciting. But the game is changing as we're moving from just performing well on a data set. You're wanting to build something that is solving an end-to-end task that has complex moving parts. Then very naturally, like the idea AJ and Tom talked about of like monitoring is very important. And as you're starting to do ongoing monitoring, you naturally discover places where the system misbehaves. And as you discover places where the system misbehaves, you'll end up discovering all sorts of issues. So for example, in the work we did over the last 4 years, as we transitioned to starting to think about real world deployments of some of our algorithms we developed for medical diagnostics, as more physicians started using them, we started discovering what were common failure points. Those failure points then motivated ways to make the algorithms more robust. And then furthermore, I think Tom talked about this idea of outlier detection, on-the-fly outlier detection. 2 years ago, in 2019, Bean Kim published this paper on this notion of like, identifying whether a prediction can be trusted or not. And in the presentation, I also talk about sort of a piece of work we did similar to that, based on identifying like real-time auditing, the ability to take, in real time. So it's almost like you have a learning algorithm that is making real-time predictions, but then you have a second learning algorithm or second algorithm whose whole job is to monitor the predictions of this algorithm. And in monitoring the predictions, it's determining whether you can be trusted or not. And in determining whether it can be trusted or not, in its own right, it can leverage all sorts of information, including susceptibility to data set shift, whether you have enough training points in your data set to even believe you could be right, and so on and so forth. And those are all things I think we just need richer end-to-end infrastructures. I mean, it kind of changes the game a little bit in AI research to move closer to what, systems people do in a way, right? They have rich, robust systems infrastructure to be able to make that happen. And now we have algorithms and systems meeting.
And in fact, this is also something that, sorry, did I interrupt you?
No. I'm actually curious, since Tom sort of seen the field evolve over time, I'm actually curious, like, does this resonate? Like, how do we do research? Like, one thing I've sort of, as I've watched this, is how do we do successfully research as investigators in this field when it's becoming more and more resource intensive, infrastructure intensive, and to do it really well, you really kind of need to have end-to-end visibility. And in my scenario, that's really meant a pretty big and ambitious research group with like 30 or so odd people at one point. That was like with collaborators, et cetera, managing it. And now some of it is part of, the company Bayesian that I manage with like a fair number of people there. So, but I think it feels a little daunting as an individual investigator to try to do all that. So I'm curious, like, if you have any ideas to share for young researchers in terms of how should they think about this.
Well, I don't know, but certainly one big trend I'm seeing is until today we still mostly test our machine learning systems by collecting test data, but I think we're seeing a move toward building a more active probing systems that in some sense are generating more informative tests than we can collect just by collecting data. I mean, this is very clear in the self-driving car world, where you might have to drive billions of hours of actual real world miles on the road, whether to find those rare cases. But maybe using computer graphics simulation and programming kind of agent-based models, you can try to create these corner cases and uncover the weaknesses of the system. And so Alan Ewell at Johns Hopkins has also been pushing this idea of that it's time for machine learning to move beyond data in some sense, particularly when we think about how we test our systems. And he works in computer vision, where you can also imagine using all the tools of computer graphics to synthesize images that will exercise our systems in important ways. So that's a big trend I see. But now, I mean, it also then again forces you to say, well, if I were trying to attack the system in some sense, puts you in the adversarial mindset, right? I think most machine learning people have been in the, I'm going for 99% correct, and now it's sort of saying, how can I break it? Is much more of a reliability engineer's mindset. But now I need maybe another person on my staff to be kind of the bad guy to think about that. So yeah, I guess I'm agreeing that it means bigger teams.
AJ, I know you have started to do some work with the ITER committee to provide guidance to engineers on this aspect.
Yeah, and I resonate both with Tom's comments and Suchi's comments about, what do we need to do, who we need to bring together to be able to move our systems to be reliable and safe. I think one point I would like to make is that it is too late to include domain experts. Once we have these systems out there, they should be working with us early on from the design stages, because even deciding things on what is the right data to focus on and what is the right objective function, and how I think Tom made this point in the chat, like the costs and what are the costs of different kind of mistakes. And of course, the user interaction is a big part of it too, because in many ways, we can tolerate some of the shortcomings of our models if we have the right user interaction. So we cannot really decouple what we are showing to the users with what these systems are doing. So that thinking of domain expertise and what we are really trying to do cannot really come at the testing stage and the continuous improvement. It needs to come there, of course, but it needs to come much earlier. The second point I would like to make is that this interaction between AI researchers and system researchers, I think, is going to be more important going forward. For example, we have started doing some work on adversarial AI, trying to look at real systems and trying to understand what kind of mitigations are possible to prevent adversarial attacks. The first observation we have is that the assumptions that the machine learning community does around what an adversarial example looks like do not really translate into the real world. In the real world, the perturbations are very different than the L2 norm around the instance. The patches, the stickers, it's just the attack modes are very different. In addition to that, we cannot really solve these problems by just changing our algorithms right now. At the moment, it's just all of those algorithmic techniques are broken. So what we come up with is actually thinking about the system level mitigations, not really machine learning mitigations, but system level mitigations about how the models and the training data are stored and encrypted, and how can we think about the adding different modules into our machine learning systems in a way that we can do real-time outlier detection and anomaly detection and have anti-spoofing in the loop and have continuous learning for those components. So just to reiterate that point, that I believe there's going to be a lot more work we need to do to think like system researchers and think about how our system architecture influences the risks we have in the AI systems. And just like a shameless plug on this, we just released an archive paper on the real world safety risks we see and these connections between machine learning and systems. So you can find that on archive, just if you want to read a little bit about our thoughts in the space.
A lot of these things that we mentioned today seem like they are converging towards like either model or system understanding. And for a long time, this problem of like understanding the model, knowing what it's doing, which features it's using, and how it will behave, has been in the interpretability and explanation domain, which is also the theme of these two sessions this morning. But somehow interpretability and robustness are not necessarily unrelated to each other. We see a lot of connections as interpretability being either a prerequisite for having a robust model or the other way around. What do you think we're missing to link these two aspects? Or is there any new approach to interpretability that focuses more into the system understanding rather than model understanding?
Well, certainly we find when we put an anomaly detector in as a second system that's monitoring the first system, the reality of anomaly detection is you get many false alarms, and so you need the it's wonderful if you can get human feedback at that point to say, oh, that's not a problem. Oh, this one is a problem, so we had a paper by my colleague Alan Fern and his student Amran Siddiqui at KDD maybe 2 years ago now, on how to harness the feedback during that anomaly detection process. Now, obviously, you want to give an explanation to the user. Here's an anomaly, and here's why I think it's an anomaly. And then the user can say, oh yes, you're right. I mean, like you're doing fraud detection, for instance, and you see this, and you say, oh yes, I definitely need to start an investigation on that case, or no, this is just a typical thing, because of course the human has a lot more contextual knowledge than the computer. There was a nice talk at ICML last week from some folks at Google on their smart buildings, and they have anomaly detectors monitoring all the sensors in the buildings, and then you're right, those alarms come up, they give them an explanation, and then they decide to create a trouble ticket or not to go fix that. So I don't know whether that is directly relevant to your question, but yeah. Definitely it's not at all useful to say, well, here's an anomaly, it's your problem. You have to say why you think it's unusual. And I assume the same thing HA goes for saying, here you made a mistake, okay, but the classifier made an error, but now the person needs to be able to say, well, okay, why did it make? You have to diagnose the cause of the error before you can fix it.
So I want to add to Tom's point, though, because it's not, I think we can think of it as like developer time to success. So if you know exactly where the error is, you're able to identify what the cause of the error is, you're able to pinpoint exactly what you need to do to fix it, then they're going to be super effective and efficient in kind of tackling the issue. Versus if you just tell them, I think there's a problem, they're going to be hunting all over the place. But I still think, to me, it feels like there isn't a white and black answer of like right now in the interpretability dialogue, I feel like a lot of the answer is interpretability is the answer to all of man's problems. And I don't think it is. Like sometimes you can build interpretable systems, sometimes you can't. And sometimes interpretable systems give you insights that are totally wrong because it's interpretable, but only in the sense that it seemingly tells you what the answer is, but it isn't exactly the answer. It's even the wrong root cause. So from my standpoint, I think there's like this soft metric we're trying to optimize, which is how do we become effective in debugging these systems faster and faster, which means and while also making it safer and safer, which means anything that allows us to identify problems is great. Anything that allows us to identify those problems and then tackle those problems faster is great. And the whole thing is a continuum, and we will need probably a whole ton of techniques to get through this, broad array of like very qualitatively broad set of goals.
So I think I just want to make the point that it really comes to how we define robustness, like come to the beginning of the discussion, right? If we define robustness to be a human-centered concept where we want to be able to reliable to user expectations and have developers in the loop to create this continuous feedback loop that our systems can gradually get better, we have to build the interface between our systems and users and developers and data providers. And I think interpretability techniques are going to be important in building that interface layer. However, I completely agree with Suchi that just thinking about any interpretability technique as a patch to solve problems we are running to is not going to be getting us there. We have to be really guided by what do we aim to gain from interpretability, and be really careful in that thinking instead of just saying that throw interpretability in there and your problems are going to be user problems, because I don't think that's what we wanna impose into the community.
Yeah, I like to say that the interpretability is just like the stack backtrace in the debugger. It's the first step, but you still have to figure out what's really going on.
Right.
And perhaps we have to figure out what is going on with the other components in the system, to error provenance, going back to the data provenance systems point of view, and close the loop. So I wish we could talk longer, and that this conversation has been really great. We will have, however, to switch to the next session, which is happening at 11. We'll have a break of 30 minutes now. The next session is going to be on interpretability and explanation, and Rich Caruana is leading the session with a great line of speakers. I want to thank Suchi, Tom, and Ajay for being with us today, and for sharing their thoughts and making us think more deeply about system reliability and robustness together with machine learning. Thanks.
Thank you, Bessa, for organizing.
Okay.
Bye.